Hey guys, so for my students, this is our very first remote lesson, so good luck. For anyone watching this, please feel free to contact me with any questions or feedback. Thank you. So today we're going to start talking about an overall topic called radical expressions. And today specifically, we're going to introduce radical expressions and talk about how to simplify basic radical expressions. So what is a radical expression? Well, it's any expression that has a radical symbol, as in a symbol like this, like a square root, right? And so radical expressions, we're talking about, things like, okay, root 40 or root 72 or the square root of 4x. You can even have variables in there, okay? So those are all radical expressions. Now, you may have dealt with radical expressions in the past, because in the past you may have dealt with equations like x squared equals 50, right? And how would you solve this? How would you get the x by itself? Well, you want to cancel this square here. So to do that, you would do what? You would square root both sides, right? So square root both sides. And then you get x is whatever the square root of 50 is. So x is around, you just plug that in your calculator and you get around 7.071. But if you think about it, this 7.071, you're kind of cutting off decimals, so it's not very precise, right? So you may also just want to say, okay, the answer is x equals whatever square root of 50 is. Exactly, x is the square root of 50. That's the answer. And so sometimes it's useful to keep things in terms of radicals so that it's more precise. So now if you think about it, we've seen two different forms of the same radical expression, right? So we took square root of 50 as an example, and we said, well, it's around this 7.071. And you can think of this as two different forms. So the first one we'll call, there's no good name for it, so we'll just say, okay, a single number under a square root. And then we took that square root of 50 and we said, well, it's around 7.071. So we took a decimal approximation of it, right? And this decimal approximation would be useful, for example, in real life. Like, let's say you were building something and you needed to measure a length of wood, let's say. You're not going to say, okay, I need square root of 50 inches of wood. No, instead, you're going to say, well, I need around 7 inches of wood and a little bit more, right? So these both have their uses, but as you get into more advanced math and science classes, you're going to be dealing with yet another form, a third form. And this third form we call simplest radical form, okay? So we're taking the same number, square root of 50, and rewriting it something like this. So there's a 5 not in the square root, but then a 2 in the square root, right? And we call this 5 root 2. So why is this third form important? Why does this exist? Well, when you're doing maybe theoretical work, or maybe you're doing work by hand, sometimes it's a little faster if you deal with this third form. And furthermore, when you're doing a standardized test, they might give you multiple choice answers in this form, right? So for example, maybe you're solving a problem and you know that the answer is square root of 50 or 7.071. But they'll give you multiple choice answers in this third form, and you will have to recognize that all three of these forms are equivalent, right? So basically, you need to be familiar with all three of these ways of presenting the same answer, and you need to be able to switch back and forth between them. So that's what we're going to be learning today, is how to convert to simplest radical form. How would you take something like root 50, right, and rewrite it to look like something like this 5 root 2? Now, I'm going to show you two different methods of doing this simplifying, okay? Now, this first method is more proper mathematically, but I think it's a little more difficult than the other method. So don't worry if this method seems a little confusing. I would just watch, and then if you like it, you can learn it that way, but also know that there's a different way coming. Anyway, the first method, I would describe it as take out the biggest square number. So what does that mean? So let's show you this method with this number, square root of 45. And so what you want to do is take out the biggest square number from 45. So what is a square number? Well, you know how if you do 2 squared, it's what? 4. 3 squared, what is that? That's 9. 4 squared, 16. You get the point, right? So these numbers, 4, 9, 16, those are your square numbers. If you keep going, 5 squared, that's 25. 6 squared, that's 36. 7 squared, that's 49, and you can keep on going forever, of course. And you ask yourself, which of these square numbers, 4, 9, 16, 25, 36, 49, which of these square numbers divides evenly into 45? This is the hard part. You want to figure out which the biggest square number is, and so you have to keep, like I'll give you problems with big numbers over here. The 45 would be a big number, and then you have to spend some time figuring out which one goes in. Then for 45, which of these square numbers is the biggest one that goes into 45? Well, that's 9, because 45 divided by 9 is a clean 5. So 45 splits into 9 times 5, and then keep the square root. That square root is still there. Okay. And then what happens next? We've taken out this 9, the biggest square number, right? What happens next is you may have learned how square roots work in a previous class, some of the properties of square roots, okay? And what you can do is when you have a square root and two numbers being multiplied inside a square root, you can split the square root. You can apply it to each thing separately. So this becomes square root of 9 times square root of 5. Now, square root of 5 is a strange, weird number. It's not an integer. It's what we call an irrational number. So this is as simple as it can get, and we're going to keep the square root of 5. But what do you notice about the square root of 9? The reason we take out a square number is because when you square root it, it's a clean integer number, right? So square root of 9, if you recall, is 3. So you apply the square root to the 9, you get a clean 3, and the square root goes away. And what you have left is square root of 5. And that right there is your final answer. Square root of 45 in simplest radical form is 3 root 5. So that's our first method of taking a single number under a square root and converting it to simplest radical form, okay? And I would say this method is more proper, mathematically speaking. So if this method makes sense to you, then by all means, keep using it. Okay? This method is going to require more understanding of what's, perfect square numbers are and how numbers divide evenly into other numbers. So there is that. Now let me show you another method of doing the same thing. So the next method is to make a tree. And if the first one was confusing, I hope the second method makes more sense. Now make a tree, so what you do, you take the square root of 45, right? You take the 45 and split it into a tree of numbers that go into 45. And you keep splitting 45 until you get it down to its basic pieces, until you can't split it anymore, basically into what we call its prime factors. So what does that mean? 45, what number goes into 45? And you can start with any number that goes into 45. I'm going to say, well, 45 ends with a 5, so 5 itself must go into 45, right? So 45 splits into 5. So 5 is a factor of 45, right? 5 times what is 45? 5 times 9. Okay, so we've split into 5 and 9. Now, can you split 5? As in, is there anything that goes into 5? And by the way, we're dealing with prime numbers, so we ignore 1. Is there anything other than 1 or 5 that goes into 5? No. So we are done with 5. But what about this 9? Can you split 9 further? Some people forget, but yes, 9 can be split further. 9 is not prime. 9 splits into 3 and 3. Now we got 5, 3, and 3. Does 3 split any further? Does anything other than 1 go into 3? No. So now we're done, okay? This is our full tree. 45 have split into what I call ending branches, 5, 3, and 3. So there's these ending branches right here, right? Now, once you're finished splitting 45 completely, so once you have a complete tree where 45 is broken down into all of its ending branches, right, its prime factors, the next thing you ask yourself is, are there any pairs of ending branches, of matching ending branches? So out of 5, 3, and 3, are there any pairs? Well, sure, our pair is a pair of 3s, right? So 3 right here, another 3 right there. That's our pair. And so what's happening with our pair here, okay, is we've just found that root 45 is actually 5 times 3 times 3, all under a square root. And we're going to take out that matching pair of 3s. What happens is we take this pair of 3s and it comes out of the square root. Now, when a pair comes out, this is like 3 times 3, so 3 squared. And to come out of the square root, you can think of the square root canceling, there being 2 3s. So what happens is you take this pair of 3s, you write it out here, but each pair only becomes 1 3. So 3 out here. And then what do we have left? The 3 has come out. We have a square root left over, and the 5 is not a pair, right? So it just hangs out in the square root. It doesn't get to come out. And now, again, this is as simple as it gets. We've taken out what we can. What we can't take out just stays under the square root. And so we've got 45 in simplest radical form. So you see, we've used this other second method to get the same result that as we did with the first method, right? And so, those two methods, that's the basics. Unfortunately, there's a lot of stuff that can go on with these two methods that we haven't seen yet. So let me show you a more complicated example and we'll see how things play out. So here's our more complicated problem. So first of all, notice that we already have a number on the outside, but we still need to simplify this huge number, 2,100, under the square root, right? So what you do is you ignore the number on the outside for now, ignore that 6, and you're going to take the 2,100 and split it. So how does 2,100 split? And you might, when you're doing problems, you might split it differently than I do, right? The end result should still be the same. 2,100, what goes into 2,100? 10 goes into 2,100, so that's 10 times 210. Now we can still split 10. What is 10 split into? 10 is 5 times 2. And then 210, you can still take out a 10 again. So here's another 10. 210 is 10 times 21. And then this other 10 you can split again into 5 and 2. And then what about 21? 21 splits into 3 and 7. So can we split any of our ending branches so far further? 5, no, that's done, that's prime. 2, that's done. 5 is done. 2 is done. 3 is also prime. 7 is prime. So now this is our complete tree right here. So what do we do next? Out of our ending branches, there's 6 of them, right? 5, 2, 5, 2, 3, 7. Where are our matching pairs? So we have a pair of 5s. And we also have a pair of 2s. And then the 3 and the 7, those are not pairs, right? So they're all on their lonesome there. And what happens is we're going to take out each pair that we found on the outside. So this pair of 5s, that's going to go out here. And the pair of 2s is going to go out there as well. So the total effect is our original problem becomes, so now don't forget there was a 6 on the outside. But then we take out a pair of 5s to get 1 5 out here. And then we take out a pair of 2s to get 1 2 out here. And then whatever ending branches are left stay around in the square root. So that's 3 and a 7, right? So 3 times 7. Now, this isn't simplified because we have some numbers that we can multiply together, right? So basically at the end, whatever numbers you took out to get on the outside, multiply them together. So 6 times 5 times 2, let's see, that's 60 on the outside, a normal 60 on the outside. And then under the square root, the guys that were left over, 3 times 7, well, so under the square root we have 21 left over. And this is, according to our tree, this is as simple as it's going to get. So 6 root 2100 in simplified radical form is this 60 root 21. So that covers the basics of these problems. And hopefully I've given you enough info to start. So what I would do here is just pause the video and kind of process what you've seen and get started, if you can, on some problems, okay, on some basic problems. So now just a quick word on some weird issues that might come up as you're doing these problems. So issues like what happens if you have more than one of the same pair? Or what if you have no pairs, no matching pairs? Or what if everything goes into a pair, you take them out and there's nothing left over? So with this first problem, square root of 162. When you split 162 into its complete tree, right, when you split it completely, you'll get something like this. And what's unusual about this is, well, what are the pairs? Well, so you got a pair of 3s here, and you got another pair of 3s here. And so both pairs have to come out, right? Like this pair comes out, that pair comes out. So just know that each pair produces 1 3 each, right? So the first pair gives you a 3 on the outside. The second pair gives you a 3 on the outside. And what do you have left? Just that 2. And so again, you have 2 pairs of 3s becomes 1 3 and another 3 on the outside, and then all you have to do is multiply them. You get 9 on the outside, 3 times 3, and then the square root of 2. Next weird case, root 30. So if you split this, you will get a tree like this. And now we've got 3 ending branches, 3, 2, 5, and you'll notice there's no matching pairs. So what happens is root 30 becomes root 3 times 2 times 5. There's no pairs we can take out, so they all just stay in the square root. And all we can do is multiply them back together again. So basically something like square root 30, it's already in simplest radical form because there's nothing we can do. So boom, what we started with is the final answer. Next up, we have 7 root 100. So if you split 100, this is what you'll get. And notice that we have 4 ending branches, and all the branches, all the branches make pairs. There's no branch that isn't in a pair, right? So you got a pair of 5s, and you got a pair of 2s. So the 5s come out, the 2s come out, everything comes out, right? You have your 7 that you started with, times the pair of 5 becomes 1 5 out here. The pair of 2s becomes 1 2 out here. And then there's no ending branches left, so you just have a square root with nothing in it. And so what happens is you multiply these numbers out here. 7 times 5 times 2 is 70. And then if you have a square root with nothing left over, it just goes away. So your final answer is a clean integer in this case. And you know, from the start, some of you may have thought, well, square root of 100 is just 10. So that's another shortcut. If all your pairs come out, that means your starting number was a perfect square already. So you could just do square root of 100. That's 10 times 7 to get 70. So that's simplifying radical expressions. Good luck with your work. Again, if you have questions or feedback, feel free to contact me.